Okay, so good afternoon, everyone. I think just to show, to a better presentation, I just wanted to use my notebook. Um, if you recall, my finite element project was to formulate a corotational shell, and then to apply that, I was going to use that to analyze castellated versus regular I-beams. And then I'm gonna try to abbreviate some of these portions, but today I'm gonna talk about the how you formulate the corrotation kinematics, and I'm gonna briefly talk about the finite element formulation, just highlights, and show you what I did in Abacus for the static case. So just to start out, so what I'm actually doing here is I'm gonna compare the element performances. So for the corrotation shell, I have this three-node triangle shell that I'll talk about in a bit, and I'm naming that S3CR, kind of just to make it consistent with Abacus naming. And then the four node quadrilateral, I'm naming that the S4CR. And then so these corrotational shells, they're going to be with large displacements, but then with small strains. But then with the abacus, that's going to be using the Lagrangian um, kinematics. And then these are S4R and S8R5. I'll explain these later on, but these will be using large strains. So before I talk about the equations, this formulation this is just based off the paper from Hagen and Philippa. They 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 formulated the shell finite elements using individual element tests method, and this was based off a free formulation. Simply, this is just to ensure that you're passing this patch test. And for finite elements, this is just kind of like a quality control, so that you have accurate solutions or it works. And then, so the stiffness matrix here will be composed of these two, the basic and higher order. And this is based off the free formulation method. And then mainly why we do this is so the basic stiffness is just to ensure that you're passing the patch test. And then the higher order stiffness is so that you have a correct rank, and then so altogether you're improving the performance of the element. And so the formulation is also based off this assumed natural strain or ANS and assumed natural divertoric strains or ANDIS. And then what this is simply is just you're increasing the flexibility of what you did for the free formulation. Um, yeah. And then I mentioned this before, but when you're separating the rigid body motion from the deformation, uh, what we're going to be using for the formulation is this shadow configuration and then this projector approach. So this shadow configuration, which I'll show you a figure for it, is it just so when you're doing a nonlinear approach, you're going to be solving the equations for the deform configuration, but then you have the current configuration and then the deform, and you also have this third configuration, which is the shadow configuration, which follows kind of your deform configuration. But there's a problem when you're solving your tangent stiffness, and what that is you're gonna get an inconsistency because technically the forces you're taking the derivative of that to get the tangent stiffness is not directly formed from that. So this projector approach, kind of from what I read, it technically resolves that so that you have a consistent tangent stiffness. And then here is just some assumptions on the 5 different ways you can do the corrotation description. With what I'm gonna do, I'm gonna just focus on this one, the consistent symmetrical self-equilibrated. And then simply what this is this just ensures self-equilibrium. So like when you're a criteria of your I guess your nonlinear finite element is you need to have a residual of 0. So it just allows us to cancel the internal force and the external force. And then this symmetry, this just ensures your tangent stiffness is symmetry, and then this maintains convergence because typically it's not symmetric. And then I talked about this already, but now let's talk about the equations. So in all, what we can start with is just when you're doing a geometric nonlinear like finite element, you have this main equation, which is the residual is just the difference between the internal forces and your external, and then you want to converge that by getting that to 0. And so in this case, we're going to do the same thing. The only difference is there's going to be extra terms on your tangent stiffness. And then, so mainly what I'm going to talk about here is how do you create this these force this correlated configuration, and then that's going to be from that shadow effect. And then how do you change your force matrices and as well as the extra terms in your tangent stiffness. So just for description, like for how I'm gonna write these equations, is everything without a tilde is in the global system, and then everything with a tilde is in the local system. And this is just a pictorial of that, where you have this initial undeformed configuration, and then this gets deformed, and then you have the third configuration, this is the shadow effect. So how the equations are going to reflect that is, so the current configuration is going to have this 0, the deform is going to have this n, and then the shadow is going to have the 0 and n subscripts. So just briefly, so this equation is telling you how you map from the current from the local to the global position, and then this t is how we're going to do that throughout. So you're going to see this a lot, and this is just a mapping. And then so here, what we see is you're going to have this rotation configuration, and then so we're using this t again to transform this rotation configuration. And then so the next thing is, how are we going to get the translation from the initial position to the deform? So we're going to use a rotation tensor, this R, and that's what I'm doing here. All right, and then the next thing is, so with that translation, we want to know now how you get the rotation. So it's just a product of these two. So that's what you see here. And so this rotation tensor is composed of two things, this n and then this theta. And this n is the rotation axis vector, which is dependent on your displacement and rotation. And then this rotation angle is also dependent on that. And so what that is in summary is just we're trying to derive this local deformation displacement vector, which is composed of your translation and then your rotation. And so how we do that is, so with all those equations, we've put it together. And then so then you get your local deformation displacement, which is just a vector. So now that you have that, we want to use I guess a principle of virtual work, or a variation. So to define our main finite element equations. So we vary the deformation displacement, and then we also vary the transformation tensor, which is the t that I was talking about. And then we also vary the rotation tensor, and then the variation of your inertial deformation translation. And then this is with respect to your inertial total displacement. So this is just getting it to the rotation tensor to the local. So now with that, we also vary the corotation deformation translation here, and then the rotation as well. And here you're going to see in the governing equations few of parameters that's going to be common. One of them is going to be this g, and this g is just so that you can transform your deformation rotation to your inertial total displacement. So this is just a transformation, so it's a relationship between these two. And then you're going to also see this other term, which is h. So this h is it's technically the derivative of your rotation, but with respect to space, so that's going to be a Jacobian term. And then you're going to see, as I mentioned before, this projector. So this projector is going to be in terms of p. So here's how they typically derive it is, so this projector tensor, you have to prove it if it's actually a true projector. And what it does is if you change the geometry of your element, then it's a mapping. You also change the forces, so it's just a mapping of that. So this p squared has to be p, and that's what I'm trying to prove here. And so with that h, you take the variation of that. And then these are just so, because we're going to be using these equations in a little bit. That's why I'm varying the h. That's why I'm varying the p. All right, so now trying to derive the internal force, the F. So as we put that together, you're going to see something familiar, but this F in linear case is just this Ke times the V, which is a stiffness and then your displacement. But then we have these extra terms. So it just maps this to the local, and then you also have the P I was talking about, the projector, and then this Jacobian of your rotation. So with that, you multiply your main linear case to get the internal force. And then now what we want to do is we want to define the stiffness terms. So what I did here is just taking the variation of the internal force, and then the product rule is imposed here. So you're going to get 4 main tangent stiffnesses and a material stiffness, and which I'm going to explain in a bit. So this material stiffness is Km, and as I said, yeah, you're going to have this P and then this H, and then you're going to multiply it by the stiffness of your local. And then the common with these stiffnesses is just this mapping terms, the T, and then transpose in the T. And you're going to see that that's going to factor out for all of them. And then so you have the second geometric stiffness, or I guess the second stiffness is the rotational geometric stiffness, KGR, and then you're going to have these terms. So the G here. Oh yeah, I didn't talk about this F term, but this F term is just your spin vector. And then and then for the third stiffness is composed of these, and then this M, and then this M it's technically your a moment vector, and then you're just mapping that using these the projector. And then this is the last, the stiffness. So you're gonna see you have this G, and then you have this spin tensor, and then the projector. So there are some additional terms, and in the paper mentioned it, but primarily they focus more on the triangle. The reason being is for the quadratic shells, you're gonna get this warping effect, warping terms, and how that gets incorporated is from the unbalanced force. So just to explain that briefly, so when you have the quadratic shell, it's flat, but then in the small strains, it remains flat relatively, but as your strains enlarge, you're gonna have like, because since this is a curved shell, you're gonna have these warping effects, and that's where the main issue is. I'm gonna see if I can figure that out, because I'm gonna try implement these additional terms. So these additional stiffnesses are here and then here. So if you put all that together, your total stiffness matrix is going to be composed of these terms that I just mentioned, and then this is just simplifying it, and then this factors out the transformation matrices, and you're only going to have these. And in summary, that's what you have for the corrotation kinematics. You have your main criteria for your residual. You have your force, where you have the stiffness, and then you have your displacements, and then the stiffness matrix, which is we just talked about. So now I'm just going to briefly talk about the finite element formulation. I'll show you more of this next time, but mainly the two. So this is the first one, the 3-node. What you do is you just derive the shape and Jacobian functions. And then since this is a shell, I'm going to show you later on how you compose the membrane and then the bending of the element. And then I think for the corrotation cases, you're going to have this extra step where you're going to fit the shadow configuration to the deformed configuration. For the triangle, this isn't really an issue, but when you get to the quadrilateral, you're going to have this extra step, which I'll talk about clearly next time. But all the other steps are going to be similar. All right, so that was everything quotational. Now, what I want to do is I'm going to use Abacus to compare the performance for the Lagrangian finite elements. So the two for the Abacus that I'm going to use is S4R and S8R5. Just briefly, I was looking at the documentation for these, and then why I'm using these elements is so I'm going to be doing both a P refinement, which is like if you're going to increase your linear to like polynomial to a quadratic, and then I'm also going to be using H refinement, which is just increasing the number of elements. So for this S4R, this is a linear shape function. You're using that to construct your element. And I found out that these are really good for stress displacements. So I'm going to be using that for some of these analyses. And this is a really good fit for large rotations and large strains. So that's what I want. And for this R here, this R here, it denotes reduced integration. So I found out what this is. So this is really efficient for 3D structures, which is what we're trying to do here. And then it's good for out of plane loading. Not so good in plane loading. So what I have for my loading cases, they're all out of plane, transverse. But oh yeah, something I wanted to add is, so I'm going to be looking at both the bending in strong axis and then weak axis, but both of them are going to be out of plane. And then so why we're using this reduced integration is so to avoid the shear and membrane locking. So if you're using this, you're not going to experience this because this is only associated with full integration. And then what this is just you're using lesser Gaussian integration points. So instead of using like multiple ones, you're just going to be integrating one point, and it's going to be at the center of like your elements. So what this does is it causes less stiffness, a less stiff element. And in a way, this is more reflected on how real life structures behave, anyways, because you're not going to have the full stiffness that you've derived in the equations. So what you can experience though, since you're using a reduced integration, is you may get this hourglass effect where because you are reducing your stiffness, so you might end up getting relatively a zero stiffness. So that's why you have this hourglass effect. But a way that you can resolve this is by doing a mesh refinement. And then there's also a way that you can do hourglass control, I think, in Abacus. So this won't be a problem for us because I'm going to be refining the mesh. And then yeah, and then for the for the S8R5, this is the features are very similar. The only two differences is this is a quadratic shape function to construct the element. And then instead of using this 5 here, is saying that we're reducing the number of nodes from, so this reduces the amount of solutions that we have to solve for, and then thereby I guess it makes it more efficient. Okay, now I'm just going to end with some of the figures and tables that I produce in Abacus. So this is for the converge fixed regular I-beam displacement. So what's shown here is just the weak axis bending, and then this is the displacement. And then for the castellated fix, this is what I have. Just one thing to note, I guess, because you have this reduced rigidity, right? I guess from the reduced fixity, and then because you have less moment of inertia because of these holes. So you can see here, this has some fixity, and this doesn't as much. And then the pin case. So this doesn't have as much fixity. They're about similar. And just to show the actual numbers for that. So what I did here is that first one that you just saw. I had like so this this H refinement. What I did is I just increased the number of degrees of freedom. And so the displacements I got are relatively small for the strong axis, and then they're large for the weak axis, right? And then so they relatively were close to each other. I did calculate the exact solution. They're kind of similar, the same magnitude. And then for the quadrilateral case, the quadratic case, and I compared it with the linear case, these are relatively the same, roughly the same, yeah. Okay, so that's pretty much what I have. And next time I'm gonna see if I can run the Abacus dynamic cases, but then I'm gonna talk about the correlated shells once I get this going. All right, thank you.